Okay, so this is a brief explainer video for our recent paper, The Disturbed Outer Milky Way Disk, recently published in Monthly Notices. The background to this is that we know that the Milky Way is significantly out of equilibrium. One of the most striking examples of this was found by Antroja et al. In 2018, where they showed that there is this phase spiral, that in the solar neighborhood, the rotational velocity of a star depends on the vertical position and vertical velocity of that star in a way that forms this neat spiral pattern. What we've been able to do since then is look at how this also manifests in other parts of the galaxy. So particularly this paper in 2021, where we looked at the galactic anticenter, that is to say, stars in the opposite direction on the sky to the galactic center, so looking towards the outer disk. We looked in that direction specifically because in that direction, the proper motion directions on the sky are equivalent to the rotational velocity of stars and the vertical velocity of stars. So doing so enabled us to look at those velocities, that velocity distribution, without relying on having a measured radial velocity, measured line of sight velocity. That meant we could use a large fraction of the stars, not just the 1% that had measured radial velocities at the time. And by doing so, we found that there is this bimodal structure, that the velocity distribution is formed of two clear lumps that I'll show again in a second. Because what we've been able to do since then is go beyond just looking at the anticenter and looking at a significantly larger range into the galactic outer disk. The reason we've been able to do that is we've said, well, yeah, when I'm looking in a different direction, the rotational velocity really isn't straightforwardly related to the proper motion velocity. So with that in mind, yes, I could restrict myself to only looking at stars that have measured radial velocities. But what I can do instead is make an approximation. And that approximation can be as simple as the radial velocity, the velocity of the star inwards or outwards from the galaxy, is small, certainly compared to the rotational velocity. And by using that approximation, we're able to work with data for a significant fraction of the Gaia stars rather than the still relatively small fraction of stars that have measured line of sight velocities. So in this paper, we looked between galactic coordinate L of 130 and 230, so a relatively decent range in the outer galaxy. The further away we get from the anticenter, the worse this approximation is, or the more reliant we are on this approximation. So that was as far as we felt comfortable in going. Here's what we found. We found that across the outer disk, the velocity distribution is still bimodal, and that this bimodality is different above and below the plane. What I mean by bimodal is that in various chunks of space, the stars tend to be either moving downwards and rotating around the galactic center quite slowly, or moving upwards and rotating around the galactic center somewhat faster. This will come across in the plot that I have shown at the bottom here, which in each panel gives rotational velocity on the x-axis against vertical velocity on the y-axis. It's split into above and below the galactic plane, and then again into radial bins between 10.5 kiloparsecs and 13.5 kiloparsecs. And what you'll see as I scroll across different ranges in L, in galactic longitude, is that this bimodal structure really comes out very strongly. It's seen at various points across this space, though it does tend to be dying away as we get to the larger L values, closer to L equals 230, for reasons that are not entirely due, or cannot be entirely due, to the difficulty in precisely measuring the velocities at that point. This comes out quite neatly again if we look at it in terms of angular momentum. So here I'm plotting angular momentum on the x-axis, which is equivalent to a guiding center radius, so an average orbital radius for a star. So I plotted the guiding center radiuses along the top here. And again, we're showing this as a function of vertical velocity, this time for just the bluest and therefore youngest main sequence stars in our population. Again, we're going to go between L of 130 and 230. And again, we're splitting above and below the plane. And you can see we can already see this break below the plane at L equals 230. It appears above the plane eventually, changes shape, changes characteristic. But then as we drift further across the galaxy towards L of 230, it started to fade away and has essentially, as far as we can tell, faded away by the time we get to 230. So that's what we've seen in the outer Milky Way. We also did some simulations to see if we could explain that a little better. Here is an example of one of those simulations where what we did was take a cold disk galaxy like the Milky Way designed to be similar to the Milky Way, and impact it with something like Sagittarius Dwarf and look at the oscillations that this provokes in the galactic disk and see how that compares to what we see. And so we can show the equivalent plots to ones I showed before for a section of this disk. And what we can show is the, again, rotational velocity against vertical velocity, again, separated out into bins between 10.5 kiloparsecs and 13.5 kiloparsecs. And what you'll see is that this does, again, at various times during our simulation, break into two clumps. So now it breaks into two clumps, and then again, and you see this recurs over time as these ripples run around the simulated galaxy. So we've not found an exact match for what we saw in the Milky Way, far from it, but what we have shown is that this is a mechanism that can produce that sort of effect. It is the details of how exactly we produce that sort of effect which make this, I think, so exciting for future study. Because kind of one of my summary points here is that, yes, the outer disk is a messy place, but the dynamics there are relatively straightforward. It's not terribly strong self-gravity. So I think that studying this region and understanding what's going on there may be key to understanding the structure and indeed recent history of the Milky Way through what has started to be called galactic seismology. My other takeaway point is more related to data analysis, which is simply that we must not be afraid to work with data where one of the measured dimensions is missing, especially in the case of Gaia data, where not relying on line of sight velocities means that we have an enormous amount more data to work with. Thank you.